Hi everybody, it's Mr. Han, and we're getting close to the end of science this year. And this week we look at how light bends when it interacts with transparent medium. So my hope is that by the end of this lesson you'll understand how light bends when it's passing from one medium to another, and that by the end of the entire set of lessons for this week, you'll understand how this bending of light can be useful in technologies like things like binoculars, microscopes, telescopes, magnifying glasses, and corrective lenses that people might wear for vision problems like nearsightedness and farsightedness and astigmatism. So recall that any substance that light can travel through is what we refer to as a medium. Okay, if there's several of them, we call them media. Okay, so a medium or a media is something that transmits light. And so we're going to be looking at this phenomenon of refraction, where light actually changes direction as it moves from one material to another. Okay, and so we're going to revisit this idea of an incident ray, but we now have a new kind of ray called a refracted ray, and that is the ray that gets bent as the light speeds up or slows down in a new material. Okay, so it shouldn't be surprising that light travels faster in things like air or empty space than it does through things like water or plastic or ice. So let's just kind of look at like an example of this. Let's say this was air. Okay, and let's say down here I have some water. So in the warm-up activity to this lesson, you would have looked at like a pencil in a glass of water. Okay, and what you would have noticed is the pencil looked very disjointed. Okay, and the reason for that is that light is actually being bent as it goes from the water into the air. Okay, we're going to actually have the light travel from the air into the water, but we can reverse the situation in the next image. So here's what it would look like. So light's traveling along in the air like this, and then it hits that interface, okay, where the water is. And I'm just going to draw my little normal line right in there, like this. Okay, there's my normal. What's going to happen is as that light comes through that interface, it's actually going to slow down and bend inwards towards where that normal line would be, something like that. Okay, the light actually changes direction. It's slowing down. So in this case, when you go from air to water, okay, light is slowing down. Okay, and the reason for that is it has to do with sort of the interaction in the material itself, the density of the material itself, and that light interacting with that material. Okay, if we flip the situation, let's have a look right here. Okay, let's say I put the water now. Let's say the light has to come through the water first, then into the air. Okay, just like we had the pencil in the water. So when you see the pencil in the water, the light has to travel through the water, and then it's going to exit the water and then come into the air. Okay, and then it's going to hit you in the eye. Okay, and the reason the pencil looks disjointed, okay, I'm going to draw my normal in real quick. Okay, there's my normal. As that light is traveling from the water and then it hits the air, all of a sudden it speeds up. Okay, and because it speeds up, it actually ends up bending away from the normal. It goes away. It's going to be traveling faster now. Okay, and so what happens is your eye might be over here looking at this. Here's your eyeball. Okay, it sees that light and thinks, oh, the pencil must be right back here because that's the line that the light is traveling to me from, when in actual fact the pencil might be like over here somewhere. So the end of my pencil might be here. Okay, your brain perceives the pencil as being here. It follows the light back, and so in that way your eye has been tricked, and that's why when you look at the pencil through the water, it looks broken. Okay, you've probably noticed this phenomenon before if you've ever gone to reach for something like in the bottom of a bathtub or in the bottom of a swimming pool, okay, or the bottom of a lake. Okay, you'll notice that it actually isn't where you think it is just based on vision. Okay, it's actually a little bit further, so it's going to look shallower than it should be because the light itself is actually being bent to look shallow. So again, if I kind of trace my line back, that makes the pencil look very shallow when in fact the pencil is way back over here. Okay, so let's kind of get a formal diagram going here. So I'm going to go back to where I had air on top, okay, and water below, like this. Okay, so this incoming ray right here is my incident ray. Just like for mirrors. Okay, it just means it's incoming, right? Okay, and over here is my normal. So that line, that dotted line down the middle, okay, just like we always do, that's our normal. And that kind of gives us like a reference line, okay, where the two lines are going to meet. And my refracted ray now, the one that's actually going to change direction, okay, so as it goes from air into water, it's actually going to move closer to the normal. It's going to look something like that. That's my refracted ray. So my incident ray was coming in, okay, when it hits that air-water interface, it slows down and bends inwards, okay, and then that's right here, this is the interface. Okay, so the interface is just where the two medium meet, okay. So again, if we kind of do this thing in a nutshell really quick, my incident ray is right here. When it hits that interface, it slows down and bends inwards, okay, and that bent line is called the refracted ray, and it's going to bend towards the normal if it slows down and away from the normal if it speeds up. So even though we know light travels in straight lines, it bends when it goes from one medium to another, okay. This refraction is due to changes in speed of light. So that's a little bit of an oversimplification, but that's kind of the best way to sort of perceive it. Okay, different mediums just slow water or sort of slow light down by different amounts, and this is what's actually called the refractive index. So the higher the refractive index, the more it slows down light. Again, we can kind of see this depth perception sort of thing with refraction here. Okay, light's traveling through the water. When it gets to the air, it's going to speed up. Okay, that's going to hit us in the eye. We're going to think the chest is right here because our eye traces the light back when in fact it's actually right here. So that's refraction sort of in a nutshell. It's this bending of light as it goes from one material to another. It's pretty simple on the surface, and what it does is it leads into a little more complicated phenomenon, which is lenses, which you'll learn about a little bit later on in the lesson. The other reason we need to know a little bit about refraction is that in the front of our eye, we actually have a lens there, and we can change the shape of that lens using the muscles around our eye. And that's what allows us to bring things into focus that are far away and things that are closer to us into focus. So we can see the words on a piece of paper or on a computer screen that might only be a few centimeters away, and we can also see people or buildings that are hundreds of meters away from us. So we have this amazing range of vision, and that's all accomplished through a lens, and that lens uses refraction to bring the light into focus. And so when we're looking at something, whether it's close or far away, what we're doing is we're stretching or contracting the lens in our eye in order to bring it into focus to change the refraction that's actually happening. We actually change its refractive index, and so we'll see a little bit about that later on in the lesson. Okay. If you have any questions about this week's material, please feel free to email me.